Look up at the night sky on a clear, moonless evening. You see the familiar sprinkle of stars, the faint glow of the Milky Way, a universe that feels vast, but somehow knowable. But what if I told you that everything we can see, all that shimmering cosmic light, is just a fraction of the real story? That for every brilliant galaxy spinning in the void, there could be another one hiding in plain sight, a ghost, a phantom, a place of profound darkness that swallows light and defies everything we thought we understood. These are the dark galaxies, and their existence challenges the very foundations of modern astronomy. It's a concept that sounds like science fiction, but it's a frontier of real science that sends a genuine chill down the spines of researchers. These aren't just empty patches of space. They are massive, structured collections of matter that somehow, bafflingly, lack the stars to illuminate them. They are the cosmic equivalents of silent, black ocean liners drifting through an invisible sea, and they force us to confront a humbling possibility that most of the universe is made of something we cannot see and do not fully comprehend. This is where exploration turns from wonder to something closer to awe, a feeling edged with a subtle, cosmic dread, because what truly lurks in the absolute darkest corners of the cosmos. Today, we are embarking on a journey into that profound darkness. We will be venturing far beyond the well-lit paths of conventional astronomy to explore 25 specific dark galaxies, each one a unique cosmic riddle. From the hauntingly quiet Dragonfly 44, a galaxy that is almost entirely dark matter, to the vast and mysterious Antlia, two lurking right in our galactic backyard, these enigmas are rewriting the rules of the universe. We'll uncover why their very existence is so unsettling to scientists, and how they are forcing us to reconsider the nature of reality itself. So get comfortable, but maybe leave a light on, as we dive into the deep space anomalies that prove the universe is far stranger and far more mysterious than we ever dreamed. Our journey into the cosmic dark begins with perhaps the most famous phantom of them all, a celestial specter known as Dragonfly 44. Nestled within the crowded Coma cluster, about 330 million light-years away, this object presents astronomers with a paradox of staggering proportions. Imagine a galaxy that possesses the sheer mass of our own magnificent Milky Way, with all the gravitational heft that implies. You would expect a brilliant pinwheel of 100 billion stars, a beacon of light visible across the universe. But Dragonfly 44 offers none of that. Instead, it emits a mere 1% of the light a galaxy of its mass should. It's a ghostly giant, a cosmic presence felt more than it is seen. The discovery, made by the aptly named Dragonfly telephoto array, a telescope built from repurposed camera lenses specifically to hunt for faint, diffuse objects sent shockwaves through the astronomical community. Here was not just a dim galaxy, but something that defied the standard recipe for what a galaxy even is. The only way to explain how this wispy collection of matter holds itself together without flying apart is to conclude that it is made almost entirely of dark matter. We are talking about a composition of 99.99% dark matter, a number so extreme it's difficult to grasp. This makes Dragonfly 44 less of a galaxy of stars and more of a colossal, invisible scaffold of dark matter, with only a tiny, almost negligible sprinkling of stars tracing out its form. This leads to the haunting classification of a failed galaxy. It appears that Dragonfly 44 had all the raw material, all the dark matter gravitational pull, to become a stellar metropolis. But for reasons we don't yet understand, the normal matter, the gas and dust that should have collapsed to form stars, never got the memo. It failed to ignite. The profound scientific fear this galaxy inspires is not just about its own strange existence, but about what it implies for our entire cosmic model. If dark matter can clump and organize itself in the structure of an entire galaxy without triggering the star formation we thought was inseparable from that process, then our understanding of galaxy formation is fundamentally incomplete, perhaps even flawed at its core. We have built our theories on the idea that dark matter provides the gravitational seeds for the bright galaxies we see. But Dragonfly 44 suggests that dark matter can build structures that remain almost entirely in the shadows, that the universe might be filled with these dark, silent hulls, and that the star-filled cosmos we observe could be just the illuminated tip of a much darker and much larger cosmic iceberg. But if Dragonfly 44 represents a ghostly giant, a failed metropolis in a distant cluster, then our next destination brings this mystery unsettlingly close to home. Drifting through the cosmic shadows on the very outskirts of our own Milky Way, there exists an object so faint, so whisper-quiet, that it was only discovered in 2018, despite being a satellite of our own galaxy. This is Segue 1, and it is less a galaxy in the traditional sense and more a cosmic fossil, a relic from the universe's deepest past. Imagine a cloud of matter so diffused that the collective light from all its stars is outshone by a single, average star in our own galaxy. Segue 1 is not just dim. It is one of the faintest and most dark matter-dominated objects ever identified. It contains only a few hundred ancient, aging stars, scattered like lonely embers in an immense, invisible cage of dark matter. The ratio is staggering. For every single pound of normal, visible matter in Segue 1, there are over 1,000 pounds of dark matter holding it all together. This isn't just a galaxy with a lot of dark matter. This is a dark matter cloud that happens to have a few stars in it. And that is precisely what makes it so scientifically terrifying. Segue 1 forces astronomers to confront the concept of a minimal galaxy. What is the absolute baseline, the barest minimum of structure, that we can still call a galaxy? Is it a brilliant spiral with billions of stars? Or can it be this a wispy, ancient collection of a few hundred stars, utterly dominated by an unseen force? If Segue 1 qualifies, then our very definition of a galaxy may be far too narrow, and the universe could be teeming with these ultra-faint, almost invisible specks, a hidden population of cosmic fossils we have only just begun to detect. But the fear and the fascination doesn't end with classification. Because Segue 1 is so pristine and so old, its stars have been orbiting within this dense dark matter halo for billions of years, since nearly the dawn of time. Their delicate motions, their tiny velocities, are like a recorded history of the gravitational field they are trapped within. By studying the subtle dance of these few ancient stars, astronomers hope to do something extraordinary. They hope to map the invisible. They hope to discern the fundamental properties of dark matter itself, whether its particles are warm, cold, or something else entirely, by seeing how they have sculpted this tiny, ancient fossil over the lifetime of the cosmos. So, Segue 1 is more than just a faint smudge on the edge of our vision. It is a living laboratory, a window back in time, and a stark reminder that some of the universe's most profound secrets are hiding, quite literally, in our own backyard. Just when we thought we had encountered the extremes of cosmic darkness, our journey takes us to a small, unassuming speck orbiting our own galaxy called Triangulum 2. This ultra-faint dwarf galaxy is so minute that for decades it was completely lost in the stellar glare of the Milky Way. But what it lacks in light, it more than makes up for in gravitational mystery. When astronomers finally managed to measure the motions of its sparse, ancient stars, they were met with a result that defied belief. These stars are moving at velocities so astonishingly high that the tiny galaxy should have torn itself apart long ago. The only possible anchor, the only force powerful enough to keep these stellar speedsters from flying off in the void, is an immense concentration of dark matter. In fact, the calculations point to Triangulum 2 having one of the highest concentrations of dark matter ever recorded relative to its size. Imagine a cosmic safe, a sphere of space so densely packed with invisible mass that the few stars within it are whipped around like marbles in a spinning centrifuge. Visualize a simulation of this: a handful of stars, mere pinpricks of light, racing in frantic orbits at thousands of miles per hour, all held in a desperate, invisible grip by a shadow that we cannot see. This incredible density is the source of a profound and unsettling scientific debate. On one side, the terrifying possibility is that the measurements are correct. If Triangulum 2 truly possesses this much dark matter, then our models for how dark matter behaves and clusters are fundamentally wrong. Our current understanding, known as the cold dark matter model, predicts a certain distribution for this mysterious substance. But Triangulum 2 seems to be breaking the rules, suggesting dark matter can clump together far more densely on small scales than anyone thought possible. This would force a complete rewrite of the cosmic recipe, implying that the invisible fabric of the universe is stranger and more complex than our most advanced physics can describe. The alternative explanation, however, is equally chilling. What if the frantic stellar motions are not a sign of stability, but of destruction? Some astronomers argue that Triangulum 2 is not a serene, dense orb at all, but a galaxy in its death throes, currently being stretched and shredded by the immense tidal forces of the Milky Way. In this scenario, the high velocities we measure are not from stars orbiting a stable dark matter core, but from stars being flung out on escape trajectories as the galaxy is ripped asunder. This would make Triangulum 2 a cosmic phantom in a different sense, not a stable dark galaxy, but a temporary, terrifying illusion. We would be witnessing its final moments, a brief snapshot of a violent dissolution that makes it appear far more massive and mysterious than it truly is. This is the core of the scientific fear surrounding this dense enigma. Both possible truths are revolutionary. Either we have found an object that breaks our understanding of dark matter's fundamental nature, or we are being fooled by a celestial mirage, a reminder of how difficult it is to interpret the faintest whispers from the cosmos. Triangulum 2 forces us to question not only what we are seeing, but our very ability to see it correctly, leaving us to wonder if we are staring at a cornerstone of a new physics, or merely watching the ghost of a galaxy fade away. And just when we thought the cosmic shadows couldn't hold any more surprises, we turn our gaze to a ghost of a different kind, a behemoth that was hiding in the most obvious place of all. Tucked away behind the dense star fields of our own Milky Way's disk, a team of astronomers made a startling discovery in 2018, a dwarf galaxy so vast and yet so faint it was like finding a cosmic cloud the size of a continent. This is Antlia 2, and its very existence throws a massive wrench into one of cosmology's most stubborn puzzles, known as the too big to fail problem. To understand why Antlia 2 is so terrifying to scientists, you first have to understand this cosmic conundrum. Our most sophisticated supercomputer simulations of the universe, which model how dark matter should clump and form the scaffolding for all galaxies, make a very specific prediction. They tell us that the Milky Way should be surrounded by a swarm of hundreds of bright, massive satellite galaxies, each one held together by a dense, powerful core of dark matter. The problem is, when we look up at the sky, we only see a few dozen of these satellites, and most of them are faint and wispy. The question has haunted astronomers for years. Where are all these predicted bright, massive galaxies? The simulations say they should be too big and gravitationally robust to fail at forming stars. Hence the name Too Big to Fail. Now enter Antlia 2, the problem child that breaks the model in a whole new way. It is a dwarf galaxy, but it's absolutely enormous, roughly the same size as the Large Magellanic Cloud, one of our brightest satellite galaxies. Yet Antlia 2 is 10,000 times fainter. It's a galactic paradox, a fluffy, diffuse monster. If you were to float inside it, you would hardly know you were in a galaxy at all. The stars are so few and far between that the night sky would appear almost empty. This incredible diffuseness is the key to the fear. How can something so massive be so ghostly? The prevailing theory is that Antlia 2 is a cosmic WIMP, a galaxy whose dark matter halo is far less dense and concentrated than our models insist it should be. This directly challenges the too big to fail problem. It suggests that maybe the missing satellites aren't missing at all. Perhaps they are all around us, but they look nothing like what we expected. They are these fluffy dark galaxies, these gigantic, ethereal structures that have failed to form stars not because they lack the mass, but because their dark matter was spread out in a way that prevented gas from collapsing to ignite stellar nurseries. The terrifying implication is that our fundamental understanding of dark matter itself may be flawed. Perhaps dark matter particles can interact with each other in ways we haven't accounted for, through forces beyond gravity, which would prevent them from clumping into the dense cores our simulations predict. Antlia 2, this colossal ghost in our backyard, is therefore more than just a curiosity. It is a living challenge, a piece of evidence that the invisible majority of our universe behaves in ways our most powerful computers have yet to simulate. It forces cosmologists back to the drawing board, confronting the humbling possibility that the rules we've written for the cosmos are incomplete, and that the true nature of reality is far more nebulous than we ever imagined. If you thought Antlia 2 was a ghostly giant, wait until you meet its equally ethereal cousin, a phantom so diffuse it seems to defy the very logic of cosmic structure. This is Crater 2, and its discovery revealed an object of such profound subtlety that it was hiding in plain sight for eons, orbiting our Milky Way just 400,000 light-years away. Imagine a dwarf galaxy so vast it spans 7,000 light-years across, making it one of the largest satellite galaxies we have ever found. Now, imagine that this colossal structure is so faint, its total light output is less than that of a single medium-sized globular cluster. Its surface brightness is almost impossibly low. If you were to place Crater 2 next to our own Milky Way in the sky, it would appear as little more than a faint, ghostly smudge, a cosmic afterthought against the brilliant stellar river. This is not just a dim galaxy, it is a low-density phantom, a wisp of a structure on a galactic scale. The sheer scale of its faintness is what sends a chill through the astronomical community. When you compare it visually to a more typical, compact dwarf galaxy, the difference is staggering. Picture a dense, sparkling sphere of stars, like a tightly packed swarm of bees, representing a normal dwarf. Now, picture Crater 2 as that same number of bees, but scattered across the volume of an entire city. The stars are so spread out, the galaxy possesses almost no central concentration. It's a uniform, ultra-faint haze, a stellar population stretched to its absolute limit. This extreme diffuseness presents a terrifying puzzle for scientists. According to our most cherished models of galaxy formation, a structure as massive as Crater 2 should be held together by a correspondingly dense, powerful halo of dark matter. This gravitational glue is what prevents a galaxy from being torn apart by the tides of its parent galaxy, or from simply dissipating into the void over time. But Crater 2's dark matter halo appears to be strangely anemic. Measurements of its stellar motions indicate a gravitational pull far weaker than expected, suggesting its dark matter is not clumped together in a dense core, but is instead spread thin, almost as if it has been diluted. This discrepancy between its expected and observed dark matter density fuels a deep-seated scientific fear. One terrifying possibility is that we are witnessing the effects of a dark matter type we do not fully understand. Perhaps dark matter particles can interact with each other through some unknown force, a kind of dark physics that allows them to scatter and spread out, preventing the formation of the dense cores our simulations predict. This would mean the invisible foundation of the cosmos is more complex and dynamic than our simple gravitational models allow. The other, equally unsettling explanation points to the destructive power of our own Milky Way. It's possible that Crater 2 is a victim of relentless galactic tides. As it orbits our galaxy, the differential gravitational pull, the same force that creates ocean tides on Earth, may be acting over billions of years to slowly but surely strip away its dark matter, pulling the invisible scaffolding out from under it and leaving the visible stars to drift apart in this vast, ghostly sprawl. If this is the case, then Crater 2 is not a stable object, but a galaxy in the process of being dismantled, a cosmic corpse we have chanced upon before it completely fades from view. This forces a profound and humbling realization. The census of galaxies we see around us may not be a static family portrait, but a single frame in a violent, dynamic movie of creation and destruction. We are left to wonder how many other such low-density phantoms have already been erased completely, their stars scattered in the halo of the Milky Way, leaving no trace of their former existence beyond a faint, lingering fear that our cosmic neighborhood is far more volatile and mysterious than it appears. While the previous galaxies have stunned us with their overwhelming dominance of dark matter, our next destination presents a problem of an entirely different, and perhaps even more unsettling, nature. What if we found a galaxy that seemed to have none at all? This is not a hypothetical question, but the core of a firestorm of controversy surrounding an object known as NGC 1052 DF2. This galaxy, found in a small group about 65 million light-years away, appears to be the exact opposite of Dragonfly 44 and its ghostly kin. Instead of being held together by an invisible hand, DF2 seems to be flying solo, a galaxy that, by all accounts, shouldn't exist. The discovery sent immediate and violent shockwaves through the field of astronomy. For decades, the entire premise of our cosmic model has been built upon a simple, foundational truth. Dark matter is the essential, invisible scaffolding upon which all galaxies are built. It provides the extra gravitational glue that prevents rotating galaxies from flying apart and explains the motions of stars within them. DF2 threw a wrench directly into this machine. Initial measurements of the velocities of its stars, and more tellingly, its bright globular clusters, revealed something astonishing. These objects were moving at a slow, sedate pace. There was no frantic racing, no need for an unseen mass to anchor them down. When astronomers did the math, the visible mass of the stars in the galaxy perfectly accounted for the gentle gravitational pull they were experiencing. There was simply no room left for dark matter. The scientific fear this triggered was immediate and profound, creating a dilemma with two equally terrifying horns. If DF2 is real and truly lacks dark matter, then our fundamental understanding of galaxy formation is broken at a foundational level. It would mean that dark matter is not always the indispensable architect we believe it to be. It opens the door to the possibility that normal matter can, under some unknown and exotic circumstances, assemble itself into a stable galaxy without the dark matter crutch. This would force a complete and radical rewrite of cosmology, a scientific revolution that would leave textbooks obsolete. The other side of the fear, however, is just as potent. What if the measurements are wrong? The techniques for weighing a galaxy are incredibly difficult, relying on precise observations of just a handful of tracers, those globular clusters, across vast distances. A small error in distance, a misidentification of which stars truly belong to the galaxy, or an incorrect assumption about the orbits of those clusters could completely skew the results. If this is the case, then DF2 becomes a terrifying lesson in our own limitations. It reveals just how perilously close to the edge of our observational capabilities we are operating when we study these faint, diffuse systems. We could be building or dismantling entire theories on the back of measurements that are, in essence, mirages. This is where the debate rages most fiercely today, centered on two key points. The first is the galaxy's distance, a number that is absolutely critical to the calculation. If DF2 is slightly closer to us than initially thought, then its stars and clusters are intrinsically fainter, meaning we overestimated the amount of normal matter present. If there is less normal matter, then the slow motions of the clusters suddenly do require the presence of dark matter to hold everything together, neatly solving the paradox, but making the galaxy far more ordinary. The second point of contention lies with the galaxy's spectacularly bright globular clusters. These clusters are unusually massive and luminous, and some researchers argue that their formation and survival might be intrinsically linked to the unique, and perhaps dark matter-free environment of DF2. Others counter that their properties are not so unusual and are simply a red herring in the larger debate. This ongoing, heated scientific battle makes NGC 1052 DF2 one of the most important objects in the modern cosmos. It is no longer just a galaxy. It has become a celestial courtroom where the very laws of the universe are being put on trial. Whether it ultimately proves to be a revolutionary exception or a cautionary tale about measurement, its legacy is already secure. It has forced astronomers to confront the terrifying possibility that the rules of the cosmos might have exceptions, and that our search for dark matter is far more complex than simply finding where it is. We must also be prepared to understand and explain the profound mystery of where it isn't. Just as the scientific community was reeling from the implications of DF2, another ghostly shape emerged from the same patch of sky, a discovery that transformed a single anomaly into a potentially terrifying pattern. This is NGC 1052 DF4, a galaxy so similar to its controversial neighbor that it appears to be its confirming twin. Found within the same sparse group of galaxies, DF4 also presented astronomers with stellar motions that were placid and slow, showing no evidence of the gravitational grip of dark matter. The discovery of a second such object was a game changer. A single outlier could be dismissed as a fluke, a measurement error, or a bizarre cosmic one-off, but a pair of them, living in the same galactic neighborhood, suggests something far more profound: the potential existence of an entire class of galaxies that somehow, unthinkably, exist without the universe's primary building block. This moves the conversation from a puzzling exception to a systematic phenomenon, a development that sent a fresh wave of apprehension through the field. The fear is no longer just about whether one galaxy can lack dark matter, but about how many more might be out there, and what their existence tells us about the rules of cosmic construction. It forces the question: if dark matter is not mandatory for galaxy formation, then what other unknown processes are at work in the universe's dark corners? This twin discovery prompted scientists to search for a common cause, a mechanism that could explain how two galaxies in the same environment could both be stripped of their invisible essence. The leading theory is as violent as it is elegant, pointing to a dramatic and catastrophic past. Imagine the serene environment of the NGC 1052 group billions of years ago. Within it, a larger, more massive galaxy, likely the dominant elliptical galaxy NGC 1052 itself, would have acted as a gravitational bully. Now envision DF2 and DF4 in their youth, each possessing a normal complement of both dark and normal matter, orbiting this central giant. As they swung close on their galactic trajectories, they would have experienced the immense and relentless pull of tidal forces. Here is where the physics becomes crucial. In a galaxy, dark matter and normal matter are not mixed uniformly. The dark matter forms a vast, diffuse halo that envelops the more concentrated core of stars and gas. During a close encounter, the pull of gravity affects these components differently. The normal matter, being collisional meaning gas clouds, can compress and slam into each other, can resist being pulled away to a certain degree. The dark matter, however, is thought to be effectively collisionless. It doesn't interact with itself or normal matter in any way other than gravity. Therefore, as the smaller galaxy passes by the larger one, the invisible dark matter halo, which is less bound to the galactic core, can be efficiently and permanently stripped away, like a ghostly cloak being torn off by an unseen hand. The visible galaxy, now robbed of its primary gravitational anchor, would be left as a fragile skeleton of stars, drifting through space as a dark matter-free relic. Visualizing this process is key to understanding its terrifying beauty. Imagine a detailed simulation showing a small, vibrant galaxy approaching a massive, glowing elliptical. As it nears, you see not the stars themselves being torn away initially, but the galaxy's invisible dark matter halo, represented as a shimmering, transparent blue aura. The gravitational tides from the larger galaxy reach out and pull this aura, stretching it into long, streaming filaments that flow away in the void. The core of visible stars, while jostled, remains largely intact, held together by its own gravity. The final frame shows the now stripped galaxy, a bare collection of stars, continuing on its orbit, its ghostly dark matter cloak left behind as cosmic debris. This theoretical narrative provides a compelling explanation, but it is far from a comfortable one. It introduces a new layer of scientific fear, because this stripping process is not something we fully comprehend or have ever directly observed in action. We are inferring it from the aftermath. The terrifying implication is that galactic evolution might be far more brutal and efficient at separating the universe's visible and invisible components than our models predicted. If this is a common occurrence in galaxy groups, then the cosmos could be littered with the stellar corpses of galaxies that had their dark matter violently removed, all of them challenging our most basic assumption that a galaxy and its dark matter halo are inseparable partners for life. The existence of DF2 and DF4 as a pair suggests we are not looking at a rare accident, but a standard, if dramatic, chapter in the life cycle of galaxies, a chapter we are only just beginning to read. But the story of dark galaxies is not only about stable phantoms or those stripped of their invisible essence. It is also a story of cosmic violence, of destruction on an unimaginable scale. Our journey now takes us to our nearest giant galactic neighbor, the magnificent Andromeda Galaxy, and to one of its most haunting satellites, a specter known as Andromeda 19. This object is not merely dim. It is being systematically torn apart, stretched into a vast, ethereal river of stars by the relentless gravitational tides of its parent galaxy. Imagine a cloud of stars, once perhaps a cohesive dwarf galaxy, now pulled and distorted into a long, thin stream that arcs through space, a celestial filament slowly unraveling. This is the terrifying reality of Andromeda 19, a galaxy caught in its death throes, and its destruction is not just a spectacular sight. It is a brutal, natural experiment that reveals the hidden architecture of the cosmos in a way nothing else can. The scientific fear here is twofold. First, we are forced to confront the violent end that likely awaits many small galaxies, a fate that may have already befallen countless others throughout cosmic history, their stars scattered and lost, leaving no trace of their original forms. It is a humbling reminder that the universe is not a static museum, but a dynamic and often destructive arena. Second, and more profoundly, the specific way in which Andromeda 19 is being shredded holds the key to mapping the invisible. As the galaxy is stretched, the motions of its stars are not governed solely by the visible mass of Andromeda. They are dictated by the shape and density of Andromeda's dark matter halo, the immense, invisible gravitational field that surrounds it. Think of it like this. If you toss a handful of glitter into a whirlpool, the way the glitter spreads out reveals the shape and strength of the unseen currents pulling it. Andromeda 19 is that glitter. By meticulously tracking the positions and velocities of its streaming stars, astronomers can work backwards to chart the precise distribution of dark matter in Andromeda's halo. They can determine whether this halo is spherical, flattened, or lopsided, and how densely the dark matter is packed at different distances from the galactic center. This is an incredibly powerful technique, but it is also where the deepest fear takes root. Our entire understanding of the large-scale structure of the universe, the famed cosmic web, is built upon a chain of assumptions about how dark matter behaves and clusters. Our models make specific predictions about the properties of these dark matter halos. If our interpretation of Andromeda 19's tidal stream is incorrect, if we misread the stellar data or make a wrong assumption about the physics of the disruption, then the dark matter map we derive from it will be fundamentally flawed. A wrong map for Andromeda's halo doesn't just affect our view of a single galaxy. It cascades upward, throwing into doubt our models for how all such giant galaxies form and interact. If the halos are shaped differently than we think, then our simulations of the entire cosmic web, the vast network of filaments and voids that defines the universe, could be built on a foundation of sand. We would be looking at a distorted reflection of reality, constructing a grand map of the cosmos based on a critical misreading of one of its key landmarks. Andromeda 19, therefore, is more than a dying galaxy. It is a celestial canary in a coal mine. Its agonizingly slow dissolution is providing us with the most direct possible probe of dark matter's distribution. But it is also holding our most fundamental cosmic models hostage to its interpretation. Getting it right is absolutely critical, and the terrifying possibility of getting it wrong means that this faint, streaming specter carries the weight of the entire cosmic web on its disintegrating shoulders. Yet even as Andromeda 19 provides a map of dark matter on a grand scale, another of Andromeda's satellites offers a more intimate, and in some ways more precise, laboratory for probing the fundamental nature of the substance itself. This is Andromeda 21, an ultra-faint dwarf galaxy that, at first glance, seems like just another member of the cosmic ghost population. It is exceptionally dim, with only a sparse smattering of ancient stars. But what makes it so special and so vital to modern physics is its extraordinary purity as a dark matter experiment. Unlike our own Milky Way, which is a chaotic mess of gas, dust, and star formation, Andromeda 21 is a pristine, quiet, and simple system. It's a place where the complications of normal matter are minimized, allowing the subtle gravitational effects of dark matter to take center stage. Scientists can study the motions of its stars with incredible precision, using them to trace the shape and density of the dark matter halo that cradles them. This galaxy isn't just an object of study. It's a controlled environment, a cosmic petri dish where the properties of the universe's most mysterious component can be isolated and measured. The fear surrounding Andromeda 21 is not one of dramatic destruction or blatant contradiction, but a much subtler, more profound anxiety. It is the fear of a slight deviation, a tiny but persistent mismatch between prediction and observation. Our standard model of cosmology is built on a very specific idea of dark matter, that it is cold, meaning its particles move slowly, and collisionless, meaning they pass right through each other and everything else, interacting only via gravity. This simple, minimalist description has been remarkably successful at explaining the universe on the largest scales. But when we look at the smallest scales, inside tiny galaxies like Andromeda 21, cracks are beginning to show. The central fear is that the dark matter halo in this galaxy might not have the exact shape or density profile that the cold, collisionless model demands. For instance, the models often predict a cusp, a sharp increase in dark matter density right at the galaxy's center. But observations of many dwarf galaxies, including possibly Andromeda 21, sometimes suggest a core, a region where the density levels off and remains constant. This tiny discrepancy, this difference between a cusp and a core, is what keeps cosmologists awake at night. If it proves to be real and widespread, it implies that dark matter is not the simple, inert substance we have assumed for decades. It could mean that dark matter particles do interact with each other through some unknown force beyond gravity. This concept, known as self-interacting dark matter, would be a revolutionary departure. Imagine if dark matter particles could collide and scatter off one another, much like molecules in a gas. This internal friction would naturally smooth out the dense central cusps predicted by the standard model, transforming them into the shallower cores we seem to observe. It would mean dark matter has a rich, complex physics of its own, a hidden sector of interactions operating completely parallel to our own visible reality. The terrifying implication is that we may have been profoundly naive in our basic assumptions. For over 30 years, the entire edifice of theoretical cosmology has been constructed on the foundation of cold, collisionless dark matter. Countless papers, simulations, and predictions rest upon this pillar. If Andromeda 21 and its kin force us to replace that simple idea with a more complex, self-interacting model, it would not be a simple tweak. It would be a paradigm shift of monumental proportions, invalidating decades of work and forcing a complete re-evaluation of how structure forms in the universe. Every simulation of galaxy formation would need to be rerun. Every prediction about the early universe would need to be rechecked. The quiet, faint starlight of Andromeda 21 is therefore shining a spotlight on one of the most fundamental questions in all of science. Is the invisible bulk of our universe simple, or is it governed by a hidden physics that we are only just beginning to sense? The answer, whatever it may be, is poised to redefine our place in the cosmos. Now, let's rewind the clock to a pivotal moment in this cosmic detective story, a time when the very idea of a dark galaxy was more speculation than established fact. This brings us to the case of Virgo 21, an object that captured the imagination of astronomers in the early 2000s and became the original poster child for the dark galaxy hypothesis. The story begins not with a faint smudge of starlight, but with the faint whisper of radio waves. Using the venerable Lovell telescope, scientists were conducting a survey of neutral hydrogen gas, the raw, cold material from which stars are born in the Virgo cluster. Amidst the cosmic noise, they found a significant and entirely unexpected clump of this gas, which they named Virgo 21. The signal was clear. Here was a massive reservoir of hydrogen, weighing in at nearly 100 million times the mass of our Sun. But when they pointed optical telescopes at the exact same coordinates, they saw nothing. No stars, no faint glow, just the empty blackness of space. It was as if they had heard the distinct and powerful hum of a ship's engine in a dense fog. But when the fog cleared, there was no ship to be seen. The immediate, electrifying conclusion was that they had found the first true dark galaxy, a vast, rotating structure of primordial gas that had, for some unknown reason, completely failed to form stars, and was being held together purely by its own dark matter halo. The implications were staggering, suggesting that the cosmos was teeming with these dark, gaseous islands. But in science, extraordinary claims demand extraordinary evidence, and the story of Virgo 21 was far from over. As more powerful telescopes, including the Hubble Space Telescope, were trained on the region, a more complex and ambiguous picture began to emerge. The gas cloud was not floating in isolation. It was located close to a well-known galaxy, NGC 4254, a galaxy that shows clear signs of a past gravitational encounter. The plot thickened when astronomers noticed that the hydrogen gas in Virgo 21 seemed to be connected to a long, faint stream of gas and stars stretching away from NGC 4254, a classic signature of a tidal tail, the kind of cosmic debris created when two galaxies gravitationally brush past one another. Suddenly, the pure dark galaxy candidate began to look like it might be a spectacular cosmic mirage. The terrifying possibility arose that Virgo 21 was not a stable, dark matter-dominated island at all, but simply a dense knot of gas that had been pulled out of its parent galaxy during a long-ago collision, a temporary and ghostly apparition with no dark matter of its own. This ambiguity sparked a fierce and ongoing debate that encapsulates the core fear in this field, the fear of being fooled by the universe itself. The legacy of Virgo 21 is not a simple answer, but a profound and cautionary lesson. It taught astronomers a humbling truth. Distinguishing a true, stable dark galaxy from a temporary cloud of tidal debris is phenomenally difficult. The observational signatures can be incredibly similar. Both can contain large amounts of neutral hydrogen gas. Both can show rotational motion, but their origins and their fates are completely different. A true dark galaxy is a fundamental building block of the cosmos, a permanent structure. A tidal debris cloud is a temporary wound, a cosmic scar that will eventually dissipate. The fear that Virgohi 21 instilled is the fear of misinterpretation. If we cannot reliably tell these two things apart, then how can we ever be sure of our census of the dark universe? Every new candidate is now viewed through this lens of intense skepticism. The initial excitement of a discovery is immediately tempered by the anxious question: are we looking at a new class of object, or are we just seeing the scattered pieces of a galactic car crash we happen to stumble upon? This ambiguity is more than just an academic headache. It leads to a deeply unsettling conclusion about the true scale of the dark galaxy population. If many of our candidates turn out to be tidal debris like Virgohi 21 might be, then the number of genuine dark galaxies could be far, far lower than we hope. Yet, if we are too cautious and dismiss a true dark galaxy as mere debris, we might be throwing away the key to understanding the universe's hidden architecture. The true number of these cosmic phantoms remains one of the most terrifying unknowns in all of modern cosmology, a number balanced precariously between revolutionary discovery and devastating observational error. Building on the cautionary tale of Virgohi 21, our search for true dark galaxies leads us to another, perhaps even more compelling, specter of gas within the same crowded cluster. This is HI 1225+01, a name that belies its profound mystery. Discovered swimming in the deep gravitational well of the Virgo cluster, this object presents a clearer, yet somehow more baffling, picture than its controversial predecessor. It is a colossal, rotating cloud of pristine hydrogen gas, weighing in at nearly 4 billion times the mass of our Sun. That is a staggering amount of raw material, more than enough to build a respectable dwarf galaxy brimming with stars. Yet, when astronomers scour its location with the most powerful optical telescopes, they find an absolute void: no stellar nurseries, no ancient star clusters, not even a single solitary spark to break the darkness. It is a cosmic blank canvas of almost unimaginable scale, a silent, swirling reservoir of potential that has, for reasons unknown, remained entirely unrealized. This sheer purity is what sets HI 1225+01 apart and elevates it to an object of intense scientific fascination and fear. The leading and most thrilling hypothesis is that we are not looking at tidal debris, but at a true protogalaxy, a dark galaxy in its very earliest stages of formation, a cosmic embryo that has yet to light up the darkness. This idea is terrifying not because of what it is, but because of the profound questions it forces us to ask about the most fundamental process in the cosmos: the birth of stars. If HI 1225+01 is indeed a pristine building block of the universe, a galactic seed frozen in time, then it directly challenges our understanding of star formation's trigger. We think we know the basic recipe. You take a massive cloud of cold gas, you let gravity do its work, pulling the gas inward until it fragments into dense clumps. And when those clumps reach a critical density and temperature, nuclear fusion ignites and a star is born. It's a process we see happening all across our own galaxy in brilliant, glowing nebulae. But this object, this vast and silent cloud, tells us that this recipe is incomplete. It possesses all the ingredients. It has the mass. It has the cold gas. It likely even has the dark matter halo providing the gravitational container to hold it all together. So why is there no star formation? The fear is that we are missing a crucial step in the cosmic cookbook, a secret ingredient without which the entire process grinds to a halt. One terrifying possibility is that the environment itself is to blame. The Virgo cluster is a notoriously hostile place, filled with hot, tenuous plasma that can act like a cosmic blowtorch. This intracluster medium, heated to millions of degrees, could be bathing the gas cloud, effectively preventing it from cooling down sufficiently to collapse. The gas may be too hot in a thermodynamic sense to condense, even though it is detected as cold, neutral hydrogen. It's stuck in a state of limbo, unable to take that final, critical step toward creation. Another, even more unsettling idea involves the need for a catalyst. Perhaps star formation isn't a spontaneous process that occurs whenever enough gas gathers. Maybe it requires a specific jolt, a shock wave from a nearby supernova, the gravitational nudge from a passing galaxy, or even the seeding of heavier elements from a previous generation of stars to help the gas radiate away its heat and contract. HI 1225 plus 01, in its primordial purity, may be too isolated and too chemically simple. Without that initial push, without those first few specks of cosmic dust to act as nucleation sites, the great gravitational cascade that leads to stars may never begin. It would be a universe forever trapped in potential, a symphony without a conductor to cue the first note. This leads to a deeply philosophical and frightening contemplation about the nature of the cosmos. Could it be that dark, gas-rich phantoms like HI 1225 plus 01 are not the rare exceptions, but in fact the rule? What if the default state for most of the universe's matter is not brilliant spiral galaxies, but these quiet, dark reservoirs? We have always assumed that given enough mass and enough time, a galaxy will naturally light up. But this object forces us to consider the opposite, that lighting up might be the difficult part, requiring a precise and delicate set of circumstances that are not always met. The profound fear is that our entire census of the cosmos, based on light, is fundamentally biased. We have been meticulously cataloging the brilliant successes of galactic evolution while potentially ignoring a vast, hidden population of cosmic failures, places where the universe simply didn't get the recipe right. These dark, gaseous phantoms could be the true silent majority, the unseen foundation upon which the rare, shining cities of stars are built. Studying HI 1225 plus 01 is therefore like looking at a fossil of the universe's earliest moments, a preserved relic that holds the secrets to why anything shines at all. Its continued silence is a louder statement than any supernova, a constant humming question mark hanging in the void, challenging us to understand why some clouds of gas become galaxies, and why others remain forever in the dark. While we often picture these dark galactic mysteries as distant, faint specters, one of the most immediate and tangible threats, or perhaps opportunities, is hurtling toward us at nearly 200 miles per second. This is Smith's Cloud, a colossal streamer of hydrogen gas over 11,000 light-years long and 2,500 light-years wide, and it is on a direct collision course with the disk of our own Milky Way. Discovered in the 1960s, it was long thought to be a relatively simple, if massive, intergalactic gas cloud, but more recent observations have revealed a far more complex and unsettling story. The cloud's trajectory and its composition point to a dramatic and violent past. It did not originate within our galaxy. It is an intruder, a celestial nomad that was likely ripped away from a smaller, external galaxy billions of years ago. The profound fear surrounding Smith's cloud is not just its impending impact, but the haunting possibility that it is not merely a cloud of gas. It could be the lingering, dark matter-rich heart of a long-disrupted dwarf galaxy. Imagine the core of a failed galaxy, stripped of its stars by a past encounter, now carrying its immense, invisible dark matter halo like a ghostly bullet aimed directly at our galactic plane. The impending collision, due to occur in roughly 30 million years, will be a spectacular, albeit slow-motion, cosmic event. When this massive reservoir of cold, dense gas plows into the Milky Way's disk, it will act like a titanic snowplow, slamming into our galaxy's own interstellar medium. The resulting shock waves will compress vast tracts of gas, triggering a firestorm of new star formation. The galactic plane will light up with thousands, perhaps even millions, of new stellar nurseries, a brilliant but temporary ring of fire in the sky. For astronomers, this presents a paradoxical mix of fear and fascination. On one hand, it offers a front-row seat to a process of galactic ecology and renewal that is usually too slow to observe. We will witness, in a single dramatic event, how galaxies can accrete fresh material from outside to fuel new generations of stars. It's a natural laboratory for studying the very triggers of stellar birth. Yet, this visible spectacle is only half the story, and it's the invisible half that fuels a deeper, more unsettling scientific anxiety. If Smith's cloud is indeed the remnant core of a dwarf galaxy, then it is not just a cloud of gas. It is embedded within its own massive halo of dark matter. And when the collision occurs, the normal matter, the hydrogen gas, will crash into the Milky Way's disk, creating a brilliant show. But the dark matter, which interacts only through gravity and not at all with normal matter, will do something entirely different. It will pass straight through our galaxy's disk, and its dark matter halo like a ghost walking through a wall. This dark matter component, which could account for the vast majority of the cloud's total mass, will simply continue on its trajectory, leaving no immediate, visible trace of its passage. We would be witnessing a profound cosmic disconnect, a brilliant star-forming firework display caused by the normal matter, while the true, massive, invisible bulk of the object, its dark matter heart, sails through our galaxy completely unseen and its effects entirely unmeasured. This leads to a terrifying question. What are the consequences of such an invisible intrusion? Could the gravitational disturbance of this dense, passing dark matter clump subtly warp the outer regions of the Milky Way's own dark matter halo? Might it perturb the orbits of distant globular clusters, or even some of our own galaxy's satellite dwarfs? We simply do not know. We lack the tools and the understanding to predict the effects of a massive, invisible object passing through another. Smith's cloud, therefore, represents a unique and urgent mystery. It is a timed experiment, set for 30 million years from now, that will test our ability to perceive the full reality of our cosmos. We will see one part of the event unfold in light, but the other, potentially more significant part, will occur in total darkness, a silent, unseen interaction in the hidden dimensions of our galaxy that we are only just beginning to map. But the cosmic shadows hold mysteries even more delicate and diminutive than the sprawling ghosts we have encountered so far. To understand the true outer limits of what can constitute a galaxy, we must shrink our perspective down to an almost impossibly small scale, to a speck of cosmic dust known as Segue 2. This object, a satellite of our own Milky Way, is so faint that it barely registers as a coherent structure at all. We are talking about a system containing only a few hundred ancient stars. To put that into perspective, A single, moderately bright globular cluster in our galaxy's halo can contain hundreds of thousands of stars. Segue 2 has the stellar population of a small stellar cluster, yet it is classified as a galaxy. This distinction is the heart of a profound and unsettling puzzle. The difference lies not in what we see, but in what we cannot. The motions of those sparse stars reveal that Segue 2 is not held together by its own meager gravity. If that were the case, the gentle but relentless tidal forces of the Milky Way, the same gravitational pull that creates our ocean tides, would have already torn this wispy collection apart, scattering its stars into the galactic halo. The fact that Segue 2 still exists as a bound object means it must be anchored by something far stronger, an immense concentration of dark matter providing the gravitational glue that its visible stars alone cannot supply. It is essentially a tiny, dense nugget of dark matter that happens to have a few stars caught within it. This presents a terrifying challenge to our understanding of galaxy formation. Our current models, which work remarkably well for large galaxies, struggle to explain how such a tiny, fragile system could form and survive. The processes of cosmic structure formation are thought to have a natural lower limit, a sort of resolution below which dark matter shouldn't be able to clump effectively. Segue 2 seems to exist below that theoretical limit. It's as if our theories are written on a coarse-grained canvas, and Segue 2 is a finely detailed brushstroke we simply don't have the resolution to paint. The fear is that our models are too simplistic, missing the intricate physics that allows dark matter to form these ultra-compact microhalos. This leads to a staggering and humbling implication. If Segue 2 represents a class of object our models didn't predict, then how many more of these microgalaxies are drifting unseen around the Milky Way and other galaxies? Our current sky surveys are biased toward finding objects that emit light. We can detect a brilliant galaxy a billion light-years away, but an object as faint as Segue 2 can hide almost in plain sight, just beyond the edge of our observational sensitivity. We have likely only found the very brightest tip of a vast iceberg of ultra-faint, dark matter-dominated systems. This hidden population could outnumber the known galaxies in our local group by an order of magnitude, a silent, invisible swarm of cosmic minutiae that represents the true building blocks of the dark matter cosmos. The existence of Segue 2 forces us to confront the terrifying possibility that we are almost completely blind to the most common type of galaxy in the universe, and that the true architecture of the cosmic web is far more intricate and finely detailed than we have ever dared to imagine. Yet, as we grapple with the profound extremes of cosmic darkness, we encounter an object that presents a different kind of challenge altogether, not one of scale or destruction, but of identity itself. Drifting in the void near our Milky Way is a faint speck known as Willman 1, a celestial entity that has thrown the very practice of cosmic classification into disarray. Is it a star cluster, a gravitationally bound collection of stars born from the same cloud of gas? Or is it a dwarf galaxy, a distinct island universe with its own dark matter halo and a unique history of formation? The answer is maddeningly unclear, and this ambiguity strikes at the heart of how we impose order on the chaotic universe. The core of the problem lies in a crucial measurement called the mass-to-light ratio. Essentially, astronomers weigh a celestial object by observing the motions of its stars, and then they compare that total mass to the amount of light the object emits. A high mass-to-light ratio is the classic signature of dark matter. It means there's far more gravitational pull present than the visible stars can account for. For Willman 1, this ratio sits in a deeply troubling gray area. It is elevated, hinting that dark matter may indeed be present, and holding this wispy collection together against the Milky Way's tidal forces. But the data is not conclusive. The measurements are so difficult, the object so faint, and the stellar motions so subtle that scientists cannot say for certain whether the extra mass comes from a dominant dark matter halo or from some other, more mundane source. This places Willman 1 directly on the knife's edge between two cosmic categories, embodying a fundamental fear in modern astronomy, that our clean, human-invented boxes for the universe are often just convenient fictions, and nature has a habit of creating messy, terrifying exceptions. This classification crisis forces us to confront the limitations of our own scientific language. We have built our understanding of the cosmos by creating definitions. A globular cluster is a dense, spherical collection of stars that form together and orbits a galaxy's core, typically with little to no dark matter. A dwarf galaxy is a smaller, gravitationally bound system of stars, gas, and dark matter that has its own independent evolutionary history. These definitions are clear in our textbooks, but Willman 1 exists in the blurry space between them. It has too few stars and is too diffuse to comfortably fit the profile of a classic globular cluster. Yet it lacks the unambiguous dark matter signature that would cement its status as a true dwarf galaxy. It is a cosmic chimera, and its very existence suggests that the universe operates on a continuum, not with strict binaries. The profound fear is that our need to categorize is blinding us to the true, complex nature of reality. By forcing every object into a predefined box, we might be missing the most interesting physics happening in the transitions, in the places where the rules break down and new laws may be waiting to be discovered. Consider the implications if Willman 1 is ultimately proven to be a star cluster. This would be terrifying in its own right, because it would mean that our understanding of star cluster formation and survival is fundamentally flawed. How could such a faint, extended cluster resist being shredded by the Milky Way's gravity without the help of dark matter? It would imply there are unknown processes of stellar dynamics or formation that we have not yet accounted for, forces that can mimic the gravitational effects of the invisible stuff. Conversely, if it is confirmed as a dark matter-dominated dwarf galaxy, it would represent one of the most extreme examples of a failed galaxy we have ever seen, a place where the dark matter scaffolding was built, but star formation was almost entirely stillborn, resulting in a system that is more ghostly halo than brilliant city. This ambiguity makes Willman 1 far more than just an academic curiosity. It is a living reminder that our knowledge is always provisional, and that the cosmos is under no obligation to conform to our neatly organized filing system. Every time we encounter an object that defies easy classification, we are being handed a gift and a challenge, the opportunity to refine our understanding, but also the terrifying responsibility to admit that our current maps of reality are incomplete, and that the true territory of the universe is far wilder and more wonderful than our categories can possibly contain. But to truly grasp the upper limits of dark matter's dominance, we must venture to a faint smudge of light in the constellation of Boots, to a cosmic specter known simply as Boots 1. This ultra-faint dwarf galaxy, a satellite of our own Milky Way, holds a record that is as profound as it is unsettling. It possesses one of the highest mass-to-light ratios ever measured in the entire universe. That technical term, mass-to-light ratio, simply means that when astronomers calculate the total gravitational mass of Boots 1, and then compare it to the puny amount of light its stars actually emit. The numbers are so wildly out of balance that they defy common sense. For Boots 1, this ratio is so astronomically high that it indicates the galaxy is made up of 99.9% dark matter. Think about that for a moment. This is not a galaxy with a lot of dark matter. This is a galaxy that is dark matter, with only a tiny, almost negligible sprinkling of ancient stars, and perhaps just a few thousand floating within it like dust motes in a vast, invisible cathedral. These stars are merely tracers, accidental markers that allow us to infer the presence of the immense, silent giant that truly dominates the space. This makes Boots 1 not just a dark galaxy, but the ultimate ghost, a place where the universe's most mysterious substance is presented in its purest, most unadulterated form, far removed from the complicating clutter of normal matter that fills brighter galaxies. For scientists, these ultra-faint, dark matter-dominated dwarfs are both a holy grail and a source of immense frustration. They are the most pristine natural laboratories we have for studying dark matter. In a giant spiral galaxy like our Milky Way, the gravitational signals of dark matter are mudded by the complex swirls of gas, the bursts of star formation, and the gravitational pull of the central supermassive black hole. It's a cosmic cocktail that is incredibly difficult to untangle. But in Boots 1, the recipe is stunningly simple. Take one immense, smooth halo of dark matter, add a handful of old, quiet stars, and stir gently over billions of years. The motions of those few stars are dictated almost exclusively by the gravitational field of the dark matter alone, offering a clear, direct signal of its distribution and density. The fear, however, is that this perfect laboratory is almost impossibly difficult to study. Boots 1 is so faint that its total light output is less than that of a single, moderately bright star in our own galaxy. Detecting it at all was a monumental achievement, but to move from mere detection to detailed analysis, to measure the precise velocities of its individual ancient stars with the accuracy needed to map the dark matter halo, pushes our very best telescopes and instruments to their absolute limits. Every photon of light we collect from Boots 1 is precious, and gathering enough data to say anything definitive requires countless hours of observation on the largest telescopes on Earth. This extreme faintness creates a terrifying bottleneck in our quest to understand the cosmos. Here we have these perfect, pristine repositories of dark matter, these cosmic ghosts that hold the secrets to the universe's most abundant substance, and they are just barely, agonizingly out of reach. We are like archaeologists who have found the perfectly preserved tomb of a lost civilization, but the only light we have is a single, flickering candle, making it impossible to read the sacred texts inside. The profound scientific fear is that the very objects that could answer our most fundamental questions are so elusive that we may never gather enough data to be certain of anything. This leads to a haunting uncertainty in the models. The slow, delicate dance of stars in Boots 1 might suggest that its dark matter halo has a soft, constant density core. But with so few stars to track, can we truly be sure? Or is the data simply too sparse, leaving us with a blurred and incomplete picture? The answers locked within Boots 1 could tell us if dark matter is cold or warm, or if its particles can interact with one another. But until we can find a way to shine a brighter light on these ultimate ghosts, the secrets of the universe's dominant material will remain tantalizingly and terrifyingly just beyond our grasp. Now, we turn our attention from the faintest ghosts to a galaxy that is actively being pulled apart before our very eyes. A cosmic spectacle of destruction that reveals the hidden violence of our galactic neighborhood. This is the Hercules dwarf galaxy, a satellite of the Milky Way that looks less like a serene island of stars and more like a celestial taffy pull. Its most striking feature is its profoundly elongated shape, a smear of ancient stars stretched across the void in a form that is anything but the neat, spherical, or elliptical shape we associate with stable galaxies. This bizarre morphology is a clear and present sign of immense gravitational stress. The Hercules dwarf is caught in the relentless tidal grip of our Milky Way, its stars being slowly but surely pulled from one end and compressed at the other as it swings around our galaxy on a punishing orbit. It is a galaxy in the process of being unspun, its very structure unraveling under forces it cannot hope to withstand. This ongoing disruption presents scientists with a terrifying interpretive challenge that cuts to the very heart of how we measure the invisible universe. When we want to weigh a galaxy and determine its dark matter content, we rely on the motions of its stars. The faster those stars move, the stronger the gravitational field holding them must be, and thus, the more dark matter we infer. But in a galaxy like Hercules, this fundamental method breaks down. The stars aren't just orbiting peacefully within a static dark matter halo. They are being violently accelerated and slung around by the Milky Way's tides. Their high velocities may not be a sign of a massive, anchoring dark matter core, but rather a symptom of their own catastrophic demise. We could be dramatically overestimating the amount of dark matter in the Hercules dwarf, mistaking the chaotic motions of a dying system for the stable rotations of a living one. This leads to a deeply unsettling fear that our entire census of dark matter in small satellite galaxies, a cornerstone of our cosmological models, could be systematically wrong, contaminated by the unseen violence of tidal destruction. Yet the second, and perhaps more profound, fear lies not in what we might be misreading, but in what is being released. As the visible stars of the Hercules dwarf are stretched into long, shimmering streams, its true bulk, its immense halo of dark matter, is undergoing the same fate, but in total silence and complete invisibility. Imagine the galaxy's dark matter halo not as a solid sphere, but as a vast, intangible cloud. The Milky Way's gravity is pulling this cloud apart, stretching it into vast, ribbon-like filaments that are winding their way through the galactic halo, weaving an invisible tapestry of pure dark matter. These streams are ghostly rivers flowing through the space around us, completely undetectable by any conventional means because they emit no light and interact with nothing. The terrifying question is, what are the consequences of these unseen structures? Could the gravitational influence of a dense, dark matter stream subtly perturb the orbits of distant stars, or even our own solar system, over billions of years? Might they act as unseen lenses, bending the light from background quasars in ways we cannot yet predict? We are only beginning to model the complex, web-like structure of these dark matter streams within our own galaxy's halo, and their presence suggests that the environment around us is far from a smooth, uniform sea of darkness. It is a dynamic, churning ocean with invisible currents and whirlpools, a hidden landscape whose features we are only just starting to imagine. The Hercules dwarf, in its agonizingly slow destruction, is therefore a double enigma. It simultaneously warns us that our measurements of the cosmos can be terrifyingly deceptive, while also revealing that the true architecture of our galactic home is being sculpted by forces we can infer but never directly see, leaving us to wonder what other invisible transformations are happening right over our heads. Just when we think we have established a clear pattern in the behavior of these cosmic ghosts, The universe presents us with a delightful yet deeply perplexing exception. Tucked away in the constellation of Leo, a faint smudge of light known as Leo T offers a completely different kind of mystery. Unlike the ancient quiescent stellar populations of Segue 1 or Boots 1, Leo T is a vibrant toddler. It is an ultra-faint dwarf galaxy, teeming with dark matter, yet it possesses a small pocket of neutral hydrogen gas that is actively collapsing to form new stars. This discovery sent a ripple of both excitement and profound unease through the astronomical community, because Leo T breaks all the established rules. It exists in a category all its own, a faint, dark matter-dominated system that has somehow retained the spark of creation long after its cousins have settled into a quiet, ancient retirement. The fear it inspires is not about destruction or absence, but about a stubborn, inexplicable vitality in a place where all our models said life should have ended billions of years ago. To understand why Leo T is so terrifyingly anomalous, you have to consider the typical life cycle of a small dwarf galaxy orbiting a giant like the Milky Way. The standard story is one of harsh environmental pressure. A small galaxy falls into the gravitational well of its massive parent. As it does so, the relentless tidal forces begin to act like a cosmic thumbscrew, exerting a pull that weakens the smaller galaxy's grip on its own gas. At the same time, if the small galaxy passes through the hot, diffuse halo of plasma that surrounds the giant, a material known as the circumgalactic medium, this superheated gas acts like a powerful wind, physically stripping the cold, star-forming hydrogen away in a process called ram pressure stripping. The result is a galaxy that is quickly quenched. Its fuel supply is cut off, star formation ceases, and it becomes a fossil, a collection of ancient stars orbiting in a dark matter halo. This is the fate we see in nearly all the other ultra-faint dwarfs. But Leo T, for reasons we cannot fully explain, has somehow dodged this cosmic guillotine. It still holds onto its gas reservoir, and that gas is not just sitting idly by. It is fragmenting and igniting into new suns. The central, chilling question is how? How has this faint, fragile galaxy managed to retain its gaseous fuel and continue forming stars in such a hostile environment? One terrifying possibility is that Leo T is a relative newcomer to our galactic neighborhood. Perhaps it has only recently, in cosmological terms, begun its first infall toward the Milky Way. It could have spent the vast majority of the universe's history in peaceful, isolated solitude, quietly nurturing its small supply of gas, only now beginning its journey into the more dangerous, crowded region of our local group. If this is true, we are witnessing a fleeting, precious stage in a dwarf galaxy's life, the final moments of its independent existence before it is inevitably stripped and quenched by its interaction with our galaxy. We are looking at a cosmic snapshot of a galaxy on the brink of a fundamental transformation, a toddler about to be thrust into a much harsher world. The fear is that our models, which are built on the fossils we see around us, have completely missed this vibrant transitional phase. We have been studying the end results of galactic evolution without understanding the delicate processes that precede it. But an even more unsettling explanation exists. What if Leo T's resilience is not due to its timing, but to its unique internal structure and the specific nature of its dark matter halo? The presence of that persistent, star-forming gas suggests that Leo T's dark matter halo is particularly robust and concentrated, providing a deep enough gravitational well to shield its precious gas from the Milky Way's stripping attempts. It may be that the density and distribution of dark matter in these small systems vary far more than we ever anticipated. Perhaps Leo T represents a class of dwarf that forms with an unusually dense, cuspy dark matter core, a fortress that can protect its internal gas long after other, less fortified dwarfs have been plundered. This directly challenges the simplified assumptions in our simulations, which often treat dark matter halos as having uniform properties for a given mass. Leo T screams that the invisible scaffolding of the universe is not uniform at all. It is rich with variation, and these variations have dramatic consequences for the visible universe they support. The terrifying implication is that the ability of a galaxy to form stars might not be a simple function of its mass or environment, but a complex dance between the specific architecture of its dark matter halo and the timing of its interactions. We are forced to admit that we do not yet understand the recipe for galactic longevity, and that a faint, seemingly insignificant speck like Leo T holds the key to a much more nuanced and complex story of cosmic evolution. Yet, as we marvel at the strange vitality of Leo T, we must also confront the opposite extreme of the cosmic spectrum, a place where time itself seems to have stood still for over 13 billion years. This is Leo IV, an ultra-faint dwarf galaxy orbiting the Milky Way, and it is less a living system than a perfect fossil, a celestial time capsule sealed during the universe's infancy. Unlike Leo T, Leo IV shows no signs of youthful vigor. It contains no gas, no dust, and no young blue stars. Its entire stellar population is ancient, composed solely of elderly suns that formed in a single, brief burst of activity within the first billion years after the Big Bang. Since that primordial dawn, Leo IV has been in a state of suspended animation, its star-forming fuel exhausted or stripped away, leaving behind a silent, red-hued relic of the cosmic dark ages. For astronomers, finding such a pristine object is like discovering a perfectly preserved archaeological site, a place where the conditions of the early universe are recorded in the chemical composition and orbital dynamics of its ancient stars. These stars are the original pioneers, forged from the pristine hydrogen and helium that filled the cosmos before heavier elements were widely scattered by supernova. They carry the chemical signature of a simpler, more pure universe, and their very existence offers a direct window into the processes that built the first galactic structures. This pristine nature is precisely what makes Leo IV, and galaxies like it, a source of such profound scientific fear. In the grand hierarchy of cosmic evidence, these ultra-faint relics are considered the ultimate arbiter, the most stringent test possible for our standard model of cosmology. The logic is compellingly simple. Because these dwarfs formed so early and evolved so little, their present-day properties, their masses, their sizes, their shapes, and their dark matter densities, should be a near-perfect reflection of the initial conditions of the universe. They are the end product of a relatively straightforward gravitational calculation, largely free from the messy, complicating astrophysics of later epochs, like supernova feedback and galactic mergers, that sculpt larger galaxies. Our most powerful supercomputer simulations of the universe are built to model this exact process. They start with the initial ripples of dark matter from the Big Bang and run the clock forward, tracing how these ripples grow through gravity to form the cosmic web and its first small halos. The simulations make very specific predictions. They tell us how many of these ultra-faint dwarfs should exist around a galaxy like the Milky Way, how massive their dark matter halos should be, and how densely that dark matter should be packed at their centers. Leo IV as a pristine relic, should be a textbook example, a data point that falls neatly onto the predicted curve. The terrifying reality is that it often doesn't, and the mismatches are anything but minor. One of the most persistent and worrying discrepancies is known as the missing satellites problem, but in a more refined and acute form. While our simulations predict a vast swarm of hundreds of dense, dark matter clumps surrounding the Milky Way, our telescopes only see a few dozen bright enough to be detected. One proposed solution was that the missing satellites are actually these ultra-faint dwarfs like Leo IV, and that we just needed more sensitive telescopes to find them. But now that we are finding them, a new, more subtle problem has emerged, the too big to fail problem in miniature. Even when we account for the faintest dwarfs, their internal properties often don't match the simulations. The dark matter halos of these observed relics seem to be less dense and more spread out, possessing chord profiles rather than the predicted cuspy ones than the robust, dense halos the simulations generate. Leo IV should be a mighty, concentrated fortress of dark matter, but observations suggest it may be a more fragile, fluffy structure. This is not a small detail. It is a direct challenge to the cold, collisionless dark matter paradigm that has been the foundation of cosmology for a generation. If the simulations are correct, then our interpretation of the data from Leo IV must be flawed. Perhaps we are misreading the stellar motions, or maybe the galaxy has been more severely shaped by tidal forces than we realize, puffing it up and diluting its dark matter. But if the observations are correct, then the simulations are wrong, and our understanding of dark matter's fundamental nature is incomplete. Perhaps dark matter is not perfectly cold and collisionless, but slightly warm, with particles that move fast enough to smooth out those dense central cusps. Or perhaps dark matter particles can interact with themselves, creating a kind of internal pressure that prevents them from clumping as densely as predicted. The fear that Leo IV embodies, therefore, is the fear of a foundational crack. This faint, ancient smudge of stars is holding our entire cosmic model accountable. Its pristine nature means there are fewer excuses, fewer complicating factors to blame for any discrepancy. A mismatch here points directly to an error in our most basic assumptions about the invisible 85% of the universe's matter. We are being forced to consider that the rules we wrote for the cosmos, rules that have been spectacularly successful at explaining the large-scale universe, might break down on the smallest galactic scales. Leo IV is a silent, ancient witness from the dawn of time, and its testimony is telling us that the story we have written about the universe's birth and evolution may require a dramatic and unsettling rewrite. But to truly understand the methods that underpin this entire field, we must turn our attention to a quieter, more methodical kind of fear, one that lurks not in the data itself, but in our interpretation of it. For this, we travel to a faint constellation of hunting dogs, Canes Venatici, and to one of its most famous residents, Canes Venatici 1. This dwarf spheroidal galaxy is a textbook example, a classic and well-studied satellite of the Milky Way that has long been held up as a pillar of evidence for dark matter. It is a ghost, yes, but a ghost we thought we knew intimately. The standard technique for uncovering its hidden mass is elegant in its simplicity, yet terrifying in its potential for error. Astronomers use the motions of its individual stars as a cosmic speedometer. By measuring the slight Doppler shifts in the light from these stars, the same effect that makes a siren's pitch change as it passes you, they can calculate how fast each star is moving along our line of sight. What they find in Canes Venatici 1 and in dozens of dwarfs like it, is a spread of velocities. Some stars are moving slowly, some quickly, all orbiting within the galaxy's gravitational field. The crucial step is to plug this spread of velocities, known as the velocity dispersion, into the equations of gravity. The result is a measurement of the total mass required to hold these stars in their orbits and prevent the galaxy from flying apart. For Cain's Venatus I1, the result is always the same. The mass required is hundreds of times greater than the combined mass of all its visible stars. This mass-to-light ratio is the direct, seemingly incontrovertible, evidence for a massive, dominating halo of dark matter. It's a measurement we have performed with increasing precision over the years, and it has become a cornerstone of our modern cosmological model. But this is where the subtle, insidious fear takes root. The entire conclusion rests on a critical assumption, that the motions we are measuring are truly representative of stars orbiting in a state of equilibrium, peacefully tracing out the contours of a static, smooth, and spherical dark matter halo. We assume the galaxy is a serene, gravitationally balanced system, a placid pond where the ripples of stellar motion cleanly reveal the pond's depth. But what if the pond is not placid? What if, instead, it is being jostled by invisible currents? The terrifying possibility is that we are misreading the stellar motions. The high velocities we detect might not be due to a vast amount of dark matter at all, but could be caused by other, more subtle astrophysical phenomena that we have failed to properly account for. One of the most potent sources of this fear involves the lingering ghosts of past mergers. Cain's Venatus I1, like all galaxies, likely formed through the assembly of smaller pieces. It's possible that it recently, in cosmic terms, consumed an even smaller dwarf galaxy or a massive globular cluster. The gravitational shock of such a merger doesn't just vanish. It can leave behind a stellar population that is still settling down, their orbits not yet circularized into the calm, equilibrium state we assume. These stars would be moving on elongated, chaotic paths, creating a temporary spike in the measured velocity dispersion that has nothing to do with the underlying dark matter halo, and everything to do with the galaxy's violent history. We would be measuring the aftermath of a cosmic digestion, not the steady state of a relaxed system, and in doing so, we could be grossly overestimating the amount of dark matter present. Another subtle effect involves the shape of the dark matter halo itself. Our models almost always assume it is a simple, smooth sphere. But what if the halo of Cain's Venatus I1 is significantly flattened, like a squashed beach ball, or triaxial, like a potato? The orbits of stars within a non-spherical gravitational field are far more complex, and if we analyze them using the simple assumption of a spherical halo, we can easily derive an incorrect mass. The velocity dispersion we measure might be accurate, but our translation of that dispersion into a total mass could be fundamentally flawed, leading us to infer a much more massive phantom than actually exists. This fear of systematic error is a quiet, methodological dread that haunts every astronomer working in this field. It's the anxiety that the entire dark galaxy problem, the paradigm that most of the universe's matter is invisible, could be less severe than we think. Perhaps these dwarfs do have dark matter, but not in the overwhelming quantities we have calculated. Maybe the excess mass is only a factor of 10, not a factor of 100. This wouldn't eliminate the need for dark matter, but it would dramatically reshape our understanding of its distribution and its role in galaxy formation. It would mean that normal matter plays a larger role in the cosmos than we believed, and that the dark universe, while still mysterious, is a slightly less dominant force. The case of Cain's Venatus I-1, the well-studied ghost, therefore becomes a profound test of our own scientific rigor. It forces us to question not just what we see, but the very lenses, both telescopic and theoretical, through which we view the cosmos. The greatest fear is not that dark matter doesn't exist, but that our confidence in its properties is built upon a foundation of assumptions that, if even slightly incorrect, could lead us far astray in our quest to map the true, hidden architecture of the universe. But to truly comprehend the outer frontier of cosmic darkness, we must push our vision to its absolute limit, to a point where a galaxy ceases to be a cohesive structure and becomes little more than a statistical anomaly. This brings us to Ursa Major 1, a satellite of the Milky Way so profoundly faint that it barely qualifies as a ghost. It is less an object and more a suggestion, a whisper of structure detected only because our most sensitive surveys manage to resolve a tiny, sparse handful of individual stars that move together through the void. If you were to take the total light output of this entire galaxy, it would be outshone by a single, average star located a few hundred light years from Earth. Its luminosity is so low that it represents the very lower bound of what our current technology can possibly identify as a coherent system. It exists at the precipice of invisibility, a collection of perhaps only a few thousand ancient suns, scattered across a volume of space that should, by all rights, be empty. This sheer, almost absolute dimness is not merely a curiosity. It is the source of a deep and unsettling scientific fear. Ursa Major 1 is not feared for what it is, but for what it represents. It is a benchmark, a data point that tells us our telescopes have finally reached the edge of their capabilities. We can see Ursa Major 1, but only just barely. The terrifying implication is that it is almost certainly not the faintest galaxy in existence. It is merely the faintest one we have been lucky enough to find. What lies beyond this detection threshold? The haunting probability is that there exists a vast, hidden population of galaxies, even darker, even smaller, and even more dominated by dark matter than Ursa Major 1. We could be surrounded by a veritable cloud of these ultra-faint specks, a cosmic plankton swimming in the dark matter halos of every major galaxy, including our own. Imagine a swarm of thousands, even millions, of such objects, each one a tiny, dense nugget of dark matter with only a handful of stars, or perhaps no stars at all, completely invisible to every instrument we have ever built. This hidden populace represents a terrifying unknown in our cosmic accounting. Our entire understanding of galaxy formation, the so-called hierarchical model, is built on the idea that large galaxies like the Milky Way were assembled from the mergers of countless smaller ones. Our simulations predict this vast swarm of dark matter subhalos. The missing satellites problem has always been the discrepancy between the hundreds of predicted satellites and the few dozen we could see. The discovery of ultra-faint dwarfs like Ursa Major 1 was supposed to solve that problem, bridging the gap between theory and observation. But the fear now is that we have only solved the problem for the brightest of the faint galaxies. Ursa Major 1 stands as a stark warning that the true population of satellite galaxies may be orders of magnitude larger than we ever imagined. If this is true, then our census of the universe is not just slightly incomplete. It is fundamentally and radically wrong. We have been constructing a model of cosmic structure based on a tiny, biased sample of the most luminous objects, while ignoring what could be the most common type of galaxy in the entire universe. This doesn't just change the numbers. It challenges our understanding of the efficiency of galaxy formation. Why do some dark matter halos manage to form a handful of stars, allowing us to detect them, while others, presumably even more numerous, form none at all? The jump from Ursa Major 1 to a completely starless dark matter halo is a small one, and the possibility that we are living in a universe teeming with these absolute phantoms, these pure dark matter galaxies, forces a profound shift in perspective. It suggests that the brilliant star-filled galaxies we study are the rare exceptions, the cosmic success stories, while the true backbone of the cosmic web is made of silent, invisible shadows, a dark majority whose presence we can only infer through its gravitational influence, and whose vast numbers we are only now, through faint messengers like Ursa Major 1, beginning to fear. Yet as we push our gaze to the absolute limits of detection, we encounter a ghost that tells a different kind of story, one not of fragility but of shocking density and a violent past. This is Ursa Major 2, another satellite of our Milky Way, but one that stands in stark contrast to the vast, fluffy phantoms like Antlia 2. While its cousin is a wispy giant, Ursa Major 2 is a dense, compact nugget of stars. Its stellar population is crammed into an extraordinarily small core, a brilliant, concentrated knot of ancient suns that shines with an intensity far greater than its diffuse surroundings. This unusual structure immediately raises a chilling question. Why is this galaxy's heart so bright and so small? The leading and most dramatic explanation is that we are not looking at a complete galaxy at all. We are looking at a galactic corpse, the stripped and ravaged heart of a system that was once far larger and more magnificent. Imagine a majestic spiral galaxy, much like a smaller version of the Triangulum Galaxy, orbiting the Milky Way in the deep past. Over billions of years, as it swung repeatedly close to our galaxy, the relentless tidal forces acted like a cosmic cheese grater. These forces have a peculiar property. They are weakest at the very center of the orbiting galaxy and strongest at its outer edges. This differential pull systematically peels away the galaxy's outskirts, shredding its faint outer stars and its encompassing dark matter halo, and scattering them into long, invisible streams. What remains after this brutal process is all that could resist being torn off the galaxy's dense, central nucleus, a core of stars so tightly bound by their own gravity that they could withstand the apocalyptic pulling. Ursa Major 2 is that surviving heart, the lone, dense relic of a catastrophic dismantling. The profound fear this inspires is that our entire census of dwarf galaxies is a gallery of celestial ghosts, and we are terrible at distinguishing the living from the dead. When we point our telescopes at a faint smudge like Ursa Major 2, we measure its properties, its mass, its dark matter content, its size, and we plug those numbers into our models of how galaxies form. But if Ursa Major 2 is a remnant, then those measurements are not a record of its birth. They are a record of its near-death experience. The dark matter profile we infer for it today is not the pristine halo it was born with. It is a ghostly echo, a scarred and truncated version of its former self. We are trying to understand the rules of galactic life by studying systems that have been fundamentally reshaped by violence. This leads to a terrifying uncertainty in one of the most heated debates in modern cosmology, the cusp versus core problem. Our pure simulations of dark matter predict that small galaxies should have a cusp, a sharp, dense peak of dark matter at their very center. But observations of many dwarfs seem to show a core, a shallower, constant density center. Ursa Major 2, as a potential remnant, throws a wrench into this debate. If its outer dark matter halo has been stripped away, The dark matter distribution we measure today could be artificially altered, perhaps making a born cusp look like an observed core. We might be misinterpreting the effects of butchery for the signature of birth. The fear is that we are building our understanding of dark matter's fundamental nature on a shaky foundation, using systems whose histories are so violent that their present state is a poor guide to their original properties. Every time we study a dwarf galaxy, we are now forced to ask a deeply unsettling question. Are we looking at a pristine building block of the universe? Or are we merely studying the scarred and battered remains of a galactic system that has already been destroyed? The silent, dense core of Ursa Major 2 offers no easy answer, only a chilling reminder that the cosmos has a violent history, and the ghosts we see today are often just the survivors of a war we never witnessed. And just as we begin to feel we have a handle on the faintest ghosts in our cosmic backyard, a new discovery emerges from the depths of modern data, pushing our understanding to its breaking point. This is Pisces 2, an ultra-faint dwarf galaxy uncovered by powerful, automated sky surveys that are methodically scanning the heavens. Its discovery is a testament to our technological progress, a faint smudge of ancient stars identified not by a lone astronomer at a telescope, but by sophisticated algorithms sifting through petabytes of digital imagery. Each new object like Pisces 2 should be a moment of pure triumph, a new piece of the cosmic puzzle falling into place. Instead, these discoveries are generating a deep and paradoxical anxiety within the scientific community. For decades, astronomers have been grappling with the infamous missing satellites problem. Our most sophisticated simulations of the universe, which model how dark matter clumps together to form the cosmic web, predict that a galaxy like the Milky Way should be surrounded by a swirling retinue of hundreds of bright, small satellite galaxies. Yet, when we looked up, we only found a few dozen. The question was simple and haunting. Where were all the missing galaxies? The initial hope was that they were simply too faint to see, and that as our telescopes improved, we would find them, neatly solving the discrepancy. And indeed, that is exactly what is happening. Ultra-faint dwarfs like Pisces 2 are the very satellites we were missing. But in a terrifying twist, their discovery hasn't solved the problem. It has transformed it into something even more baffling. We are now facing what some scientists are calling the too many satellites problem. The newest, deepest surveys are finding so many of these ultra-faint specks that they are beginning to overproduce the number of small galaxies compared to the simplest versions of our models. It's a cosmic case of damned if you do, damned if you don't. Before, we didn't have enough satellites. Now, we might have too many of a certain kind. This isn't a solution. It's a sign that our physics is fundamentally wrong. The core of the fear lies in the nature of the simulations themselves. They are not arbitrary. They are built upon the bedrock principles of our standard cosmological model, which includes specific assumptions about the properties of dark matter, namely that it is cold and collisionless. When we run these simulations with this specific recipe, they produce a certain distribution of dark matter halos around a Milky Way-like galaxy. This distribution has a particular shape when plotted on a graph, a smooth curve that predicts how many halos of each mass should exist. The original missing satellites problem was that the observed number of bright satellites fell far below this curve. Now, with the discovery of Pisces 2 and its ultra-faint kin, we are finally populating the lower end of that curve, the realm of the tiniest, least massive halos. But the curve itself seems to be the wrong shape. The simulations may not create enough of the very smallest halos to account for the swarms of ultra-faint dwarfs we are finding. Or they may create them, but with properties that don't match the real galaxies. Pisces 2, therefore, is more than just another ghost. It is a data point of profound dissonance. It tells us that the invisible scaffolding of our universe might be clumpier on small scales than our standard model allows. This forces cosmologists toward a terrifying crossroads. One path leads to the possibility that dark matter is more complex than we thought. Perhaps it is not perfectly cold, but slightly warm, meaning its particles move at a significant fraction of the speed of light. This warmth would suppress the formation of the very smallest dark matter clumps, potentially bringing the simulated numbers back in line with the observed count of ultra-faint dwarfs like Pisces 2. Another, even more radical path suggests that the rules of gravity itself need modification on galactic scales, a theory known as MIND, though this brings its own host of immense challenges. The discovery of each new ultra-faint dwarf galaxy is like adding another grain to a scale, and the balance is tipping in a direction that none of our simple models predicted. Pisces 2 represents the new frontier, not of discovery, but of contradiction. It is a clear signal that we are not merely missing pieces of the puzzle. We may be trying to force the pieces we have into a picture that doesn't match the reality of the cosmos. With every faint galaxy we add to the map, the comfortable certainty of our models erodes, replaced by the thrilling yet terrifying realization that the universe is demanding a more sophisticated set of rules, rules that we have only just begun to imagine. While many of the dark galaxies we've explored represent stable, if ghostly, structures, our next destination offers a far more dynamic and violent spectacle. This is Hydra 2, a dwarf galaxy satellite of the Milky Way that is not merely dark, but actively dying before our very eyes. Observations reveal a system stretched and distorted into a teardrop shape, a classic and unmistakable signature of a galaxy caught in the relentless tidal grip of a much larger predator. The scientific fear surrounding Hydra 2 is not about what it is, but what we are witnessing, the real-time death of a galaxy. This isn't a historical event inferred from fossils. It is an ongoing celestial autopsy, and the process is turning out to be far messier and far less predictable than any of our elegant computer simulations had led us to believe. We thought we understood the basic mechanics of tidal disruption. The theory is straightforward. As a small galaxy like Hydra 2 orbits the Milky Way, the gravitational pull on the side closer to us is stronger than the pull on the far side. This difference, the tidal force, stretches the galaxy, pulling it apart like cosmic taffy. The models predicted a relatively clean and symmetrical process, with stars being stripped away in smooth, predictable streams. But Hydra 2 tells a different story. Its disintegration appears lumpy and asymmetric. Instead of a single, graceful river of stars flowing away, we see clumps and knots, as if entire chunks of the galaxy are being liberated in violent, discrete events. This messiness forces a terrifying admission. Our understanding of galactic dynamics is still primitive. We are learning that the death of a galaxy is not a serene, linear unraveling, but a chaotic and clumpy dissolution, full of complexities that our current physics struggles to capture. The most profound and unsettling consequence of this disruption, however, involves the galaxy's invisible component. Hydra 2, like all galaxies, was born within and bound by a massive halo of dark matter. This invisible scaffold provided the gravitational glue that held its stars together and dictated its rotation. But as the Milky Way's tides rip apart the visible stars of Hydra 2, they are doing the exact same thing to its dark matter halo. Imagine the dark matter not as a solid sphere, but as a vast, intangible cloud. The tidal forces are now stretching this cloud, pulling it apart and scattering it into a vast, diffuse, and invisible stream that is winding its way through the halo of our own galaxy. This is the ultimate scientific fear. We are watching the dark matter that once constituted a coherent galactic structure be released back in the wild, so to speak, and we have almost no way to track it. We can see the stars being stripped away because they emit light, giving us a tracer for the disruption. But the dark matter, by its very nature, leaves no such trail. It is a ghost being released from its haunt, silently merging with the greater ghost of the Milky Way's halo. We are witnessing a fundamental transformation of the cosmic landscape, but we are blind to the fate of its most massive component. We don't know how quickly this dark matter is being scattered, how it is mixing with our galaxy's own dark matter, or what its final distribution will be. This isn't just an academic concern. It strikes at the heart of our attempts to map the true mass distribution of our own galactic home. If we cannot account for these incoming streams of shredded dark matter, our models of the Milky Way's gravitational field will always be incomplete, and our predictions for the motions of distant stars and satellite galaxies will contain hidden, terrifying errors. This leads to a chilling realization about the history of our cosmic neighborhood. Hydra 2 is not a unique event. It is likely a common, recurring chapter in the life of a large spiral galaxy like our own. Over billions of years, the Milky Way has probably consumed hundreds of smaller dwarfs, each one adding its stars and, crucially, its dark matter to our galaxy's halo. The visible stars from these mergers eventually phase mix, becoming indistinguishable from the native stellar population. But the dark matter from these events does not mix in the same way. Because it doesn't collide or interact, it doesn't smooth out. Instead, it is thought to remain in faint, tangled streams and clouds, creating a complex, lumpy, and invisible topography within the halo. We are only just beginning to infer the presence of these dark matter substructures through their subtle gravitational effects. The ongoing destruction of Hydra 2 provides a rare, visible anchor point for one of these events. It is a living example of how the Milky Way grows not just by accreting stars, but by cannibalizing the invisible scaffolding of its smaller neighbors. The fear is that our galaxy's dark matter halo is not the smooth, featureless sphere often depicted in models, but a chaotic graveyard of digested galaxies, a ghostly archive of past violence that we are only now learning how to read. The final, haunting lesson of Hydra 2 is that galactic death is not an end, but a transformation. The galaxy as a distinct entity ceases to be, but its essence, its stars, and most importantly, its dark matter, is recycled, becoming part of the larger organism that consumed it, forever altering the hidden gravitational landscape of our cosmos in ways we are only beginning to fear. Just when we think we have categorized these dark galaxies as quiet, sterile places, the universe delivers a stunning surprise that turns our assumptions on their head. This brings us to Reticulum 2, an ultra-faint dwarf galaxy so small and remote it was once considered little more than a cosmic afterthought. But hidden within its sparse population of ancient stars lies a secret of cosmic alchemy so profound it has redefined our understanding of where the universe forges its most precious elements. Reticulum 2 is not just a dark galaxy. It is a celestial treasure chest, overflowing with a shocking abundance of heavy elements like gold, platinum, and uranium. These are not just any metals. They are the products of the most violent and rare events in the cosmos, the cataclysmic mergers of neutron stars. The profound scientific fear surrounding Reticulum 2 has nothing to do with an absence of dark matter. but with an overwhelming presence of starlight that tells a terrifying story of a sudden, apocalyptic birth. For astronomers, this faint smudge in the southern sky has become a smoking gun, proving that these seemingly tranquil, dark matter-dominated islands are capable of hosting the most extreme physics imaginable. And we are left with the chilling realization that we have no idea how such a colossal explosion could be triggered in such a tiny, fragile system. To grasp why Reticulum 2 is so terrifyingly unique, you have to understand the cosmic origins of the elements. The universe began with only the lightest elements: hydrogen, helium, and a trace of lithium. Everything else, the iron in your blood, the calcium in your bones, the oxygen you breathe, was forged later in the hearts of stars. But there is a limit to what even the most massive stars can create. Elements heavier than iron, like gold, platinum, and neodymium, cannot be made in the steady nuclear fusion of a stellar core. They require a cataclysm, an environment of almost unimaginable neutron flux, where atoms are bombarded and built into heavier forms in a frantic process known as rapid neutron capture, or the R process. For decades, astronomers debated the primary source of these heavy elements. The two leading candidates were the violent deaths of massive stars in supernova and the even more extreme collisions between the densest objects in the universe, neutron stars. A single neutron star merger can unleash a firestorm of nuclear reactions, spraying out staggering amounts of gold and other R-process elements across space. The discovery of Reticulum 2 provided the most compelling evidence to date that these rare mergers are indeed a primary cosmic forger. The stars in this dwarf galaxy are not just mildly enriched with these heavy elements. They are absolutely laden with them. The signature is so strong and so uniform across the galaxy's stars that it points to a single, colossal event that polluted the entire system in one go. Imagine a pristine, primordial galaxy, a cloud of pure hydrogen and helium gas, quietly orbiting in the early universe. Then, in a flash of incalculable energy, a pair of orbiting neutron stars in its course spiral inward and smash together. The resulting kilonova explosion is so brilliant, it briefly outshines all the stars in the galaxy combined. And in that fleeting moment, it seeds the entire galactic gas cloud with a rich dusting of newly forged gold, platinum, and other rare earth elements. The next generation of stars that forms from this enriched material then carries the chemical fingerprint of that one singular cataclysm. This is what we are seeing in Reticulum 2, the fossilized record of a single, glorious, and terrifyingly powerful event. This leads directly to the core of the scientific fear. How does a tiny, ultra-faint dwarf galaxy, with a total mass thousands of times less than that of the Milky Way, manage to host and trigger such an extraordinarily rare event? In a large galaxy like our own, neutron star mergers are thought to be uncommon, happening perhaps once every 10,000 to 100,000 years. But the Milky Way contains hundreds of billions of stars, a vast stellar population that makes the statistics work. For a small system like Reticulum 2, which contains only a few known stars, the probability of forming not just one, but two massive stars in a binary pair that live, die, and leave behind neutron stars that then spiral together and merge is astronomically low. It's like a small, isolated village with a population of 100 people, somehow producing two Nobel Prize winners, who then decide to collaborate on a world-changing invention. The odds seem impossibly long. This forces a terrifying reconsideration of the conditions inside these dark matter halos in the early universe. Perhaps the environment was radically different. Maybe the initial generation of stars in these small systems was top-heavy, meaning it produced an unusually high number of very massive stars that quickly evolved and died, leaving behind a dense population of neutron stars. In this crowded stellar nursery, dynamical interactions, close gravitational encounters between these dense remnants could have forced binary pairs to merge on shockingly short timescales. Instead of taking billions of years to spiral together through gravitational wave emission, a chance gravitational slingshot could have hurled two neutron stars into a collision course in just a few million years. The fear is that our models of star formation and stellar evolution, which are largely calibrated from what we see in the Milky Way, may be completely inapplicable to these tiny, intense, and isolated systems. Reticulum 2 suggests that the early universe was a patchwork of wildly different galactic environments, and in some of these dark, quiet corners, the conditions were just right to concentrate and detonate the universe's most powerful bombs. The implications of this extend far beyond this one dwarf galaxy, reaching into the very fundamentals of cosmic chemistry. If small, dark galaxies like Reticulum 2 were the dominant sites for our process element production in the early universe, then the chemical enrichment of the entire cosmos would have followed a much lumpier and more unpredictable path than we ever imagined. Instead of a slow, steady pollution from frequent supernova in large galaxies, the process may have been dominated by these rare but incredibly productive golden eruptions in tiny systems. These enriched dwarfs would then have been gravitationally captured and absorbed by larger galaxies like the Milky Way, seeding them with their precious metallic cargo. This means that the gold in your jewelry or the platinum in a catalytic converter may have originated not in our own grand galaxy, but in the long-vanished heart of a tiny, dark galaxy that was consumed billions of years ago. Reticulum 2 stands as a preserved relic of that era, a time capsule showing us that the seeds of complexity, the very elements that make rocky planets and life itself possible, were scattered across the cosmos by violent, unpredictable explosions in the universe's smallest and darkest habitats. The galaxy's faint starlight, therefore, illuminates a terrifying and beautiful truth, that the quietest places can host the loudest events, and that the foundations of our material world were forged in cataclysms that we are only now, through the study of these cosmic ghosts, beginning to understand. And so we arrive at the final, and perhaps most profound, mystery of all the dark galaxies we haven't found. We have journeyed through a gallery of phantoms, from failed giants and stripped skeletons to ancient fossils and golden-tinged relics. But these 25, for all their strangeness, share one crucial trait. We were able to detect them. They gave us some small signal, a handful of ancient stars, a whisper of radio waves from hydrogen gas, a subtle distortion in the gravitational field. They are the ghosts that, for a fleeting moment, stepped into the light. The ultimate scientific fear is that these are not the main event. They are merely the faint, visible echoes of a much deeper and more pervasive darkness. The true rulers of the cosmic landscape may be the ones that offer no signal at all. The galaxies that are, by their very nature, completely and utterly invisible to every instrument we have ever built or even conceived. Consider the possibility of a primordial dark galaxy, a structure that formed in the universe's first few 100 million years. In that ancient, dense era, dark matter halos could have collapsed, creating the gravitational seeds for galaxies. But what if, in some of these halos, the conditions were never right for the first stars to ignite? The gas might have been too hot or too diffuse, Or perhaps it was prevented from cooling by the intense background radiation of the young cosmos. These structures would have remained pure dark matter halos, islands of invisible mass adrift in the darkness of the cosmic dawn. They would have no stellar populations to age, no gas to be stripped, no elements to enrich. They would be frozen in their initial state, pristine relics of the universe's first structures, but with no handle for us to grasp. Our telescopes, which rely on light from stars or the radio signature of gas, would sweep right over them, completely unaware of their existence. They are the ultimate cosmic fossils, but they are buried in a darkness so complete we have no way to dig them up. Then there is the more radical, yet equally plausible, concept of a galaxy made entirely of dark matter. Not 99.9% like Boots 1, but 100%. A vast, swirling structure of dark matter particles, bound together by their own gravity, with not a single atom of normal matter, no gas, no dust, no stars anywhere within it. Such an object would be the purest expression of the universe's dominant substance. A phantom so perfect it would be utterly undetectable by any electromagnetic means. It would not absorb light, it would not emit it, and it would not block it. It would be completely transparent. The only way we could ever infer its presence would be through its gravity, and even that is a terrifyingly difficult prospect. If such a pure dark galaxy were to drift in the empty void between major galaxy clusters, its gravitational influence would be so isolated and subtle that we would have no background objects to use as reference. It would be like trying to detect a silent, black submarine in the middle of the deepest, darkest ocean by only the slight tug it exerts on the water around it. A tug that is lost in the vast, churning currents of the cosmic sea. This leads to the greatest and most humbling fear that permeates the entire field of cosmology, that the 25 dark galaxies we have catalogued are not the exception, but the rare, flawed exceptions that we were lucky enough to find. They are the ones that, through some cosmic accident, retained a tiny trace of normal matter, a few stars, a wisp of gas, that betrayed their presence. For every Dragonfly 44 with its 1% of starlight, there could be 1,000 identical dark matter structures that formed 0 stars and remain in total blackness. For every Virgohi 21 with its controversial cloud of hydrogen, there could be 10,000 pure dark matter halos that never captured any gas at all. The sheer scale of this potential hidden population is what sends a genuine chill through the scientific community. Our entire understanding of the cosmos is built upon what we can see. We have meticulously mapped the luminous cosmic web, the brilliant filaments of galaxies and clusters that stretch across the void. But what if that glorious, shining structure is just a delicate tracing of glitter on the surface of a much larger, much more massive, and completely invisible framework? What if the universe we see is merely the decorative lighting on a building whose true size and shape are hidden in shadow? This isn't just a philosophical musing. It has concrete, unsettling consequences for our fundamental models. The amount of dark matter we infer from the motions of galaxies and the bending of light from distant quasars is a fixed number. That mass has to be distributed somewhere. Our current models assume it is smoothly spread through the halos of galaxies and clusters. But if a significant fraction of that dark matter is locked up in these invisible, isolated clumps, in a vast population of pure dark galaxies, then our maps of the cosmic mass distribution are fundamentally wrong. The dark matter environment around us would not be a smooth sea, but a chunky soup, filled with invisible islands and continents that subtly warp the paths of light and the motions of stars in ways we haven't accounted for. We might be trying to solve the cosmic puzzle with a significant number of the pieces missing, and worse, we don't even know how many pieces are gone. The true architecture of the universe, the dark matter skeleton that dictates the growth and evolution of everything we hold visible, may be infinitely more complex and richly structured than our most powerful simulations can portray. The ultimate fear is not that dark matter exists, but that most of it is organized into forms that are, and may forever remain, completely and terrifyingly beyond our perception. We are left with the haunting realization that we may only ever study the faint, luminous crumbs fallen from a table set in a dark room, a room whose true scale and contents we can only guess at, and whose silent, invisible occupants fundamentally shape the reality we call home. And so our terrifying journey through the shadows comes to a close. We have ventured from the ghostly giant dragonfly 44 to the ancient fossil of Leo IV, from the controversial emptiness of DF2 to the golden-laden relic of Reticulum 2. We have witnessed galaxies being shredded, galaxies failing to ignite, and galaxies that might not even be galaxies at all. Each one of these 25 cosmic phantoms, in its own unique way, has served as a stark challenge to the very foundations of our knowledge. They are not merely curiosities. They are living, breathing, or perhaps not breathing contradictions. They force us to question the nature of dark matter, the unshakable laws of gravity, and the grand narrative of how galaxies are born, live, and die. The fear they inspire is not the fear of a monster lurking in the dark. It is a far more profound and unsettling dread, the fear of our own ignorance. It is the humbling realization that the universe operates on a scale, and with a complexity that consistently defies our most brilliant theories and powerful simulations. We built a model of the cosmos, a beautiful, mathematically elegant framework, and these dark galaxies have stepped forward, one by one, to point out the cracks in its foundation. They are the universe's way of reminding us that our map is not the territory, that our understanding is always provisional, and that for every question we answer, a dozen more, far more terrifying in their implications, rise up to take its place. So the next time you find yourself under a clear, star-filled night, take a moment to truly look up. See the familiar constellations, the steady glow of the planets, the soft river of the Milky Way. But now, I hope you will also see the emptiness between them differently. Remember that the darkness is not empty. It is filled with invisible giants, with failed universes, with silent, swirling phantoms that hold the keys to the greatest mysteries of all. They are out there right now, shaping the cosmos from the shadows, and their silent presence is the most compelling reason we have to keep looking, to keep questioning, and to never stop being awestruck by the sheer, magnificent strangeness of it all. We would love to hear which of these dark galaxies captured your imagination the most. Was it the colossal, fluffy ghost of Antlia 2, hiding in our backyard? Or the impossible, star-forming toddler Leo T, perhaps the ultimate phantom, Boots 1, sent a chill down your spine? Let us know in the comments below which one you find the most frightening or the most fascinating, and why. Your curiosity is what fuels this incredible journey of discovery.